In this clip we're going to be looking at different types of glacial landforms and what those landforms look like on a topographic map. Now, wherever glaciers have existed today or in the recent geologic past, they have profoundly shaped the landscape that we see, because glaciers are very powerful eroders and transporters of sediment and geologic materials. This map, this is the same portion of the map that's used in the lab instructions. This shows the Logan Pass area in Glacier National Park, which is in north central Montana. Here the Rockies are composed of relatively soft but ancient sedimentary rock layers into which Ice Age glaciers heavily eroded this landscape, leaving behind a variety of terrain features characteristic of alpine glacier erosion. Most notable is the cirque. A cirque is a broad, bowl-shaped depression eroded into the mountainside by an alpine glacier. There are many fine examples of cirques in the map area. And you recognize the cirque by having U-shaped contours that are open in the down glacier direction. Cirques form the head of broad U-shaped valleys eroded by large valley glaciers. This cirque is left hanging because notice the elevation drop at the mouth of that cirque. This is, in other words, this cirque forms a hanging valley that's perched well above the main valley floor because it was carved or eroded by a smaller glacier with less erosive power. Where cirques erode a mountain from multiple sides, what we're left with is a horn, a pyramid-shaped mountain peak formed by cirque erosion on 3 or 4 sides of the mountain. Reynolds Mountain is a great example of a horn, as is Clements Mountain. Clements is a 3-sided horn, whereas Reynolds is 4-sided. Reynolds was carved by cirque glaciers on 4 sides. Clements is the erosional remnant of 3 cirque glaciers working against the mountain. Cirques are separated by narrow knife-edge ridges called arêtes. We see a number of fine examples of arêtes in the map area. Arêtes are mountain ridges that divide cirques. Where glaciers start to cut all the way through the intervening ridge, we're left with a shallow depression called a col. In other words, a col is where cirque glaciers eroded all the way through a mountain from 2 sides. Finally, cirques often have depressions at the bottom now filled by lakes. Those lakes are given a special name. They're called tarns. So we have a number of cirque glaciers were eroding this area during the Ice Age, leaving behind these bowl-shaped depressions with U-shaped contours open in the down glacier, down valley direction. Steep contours form the cirque headwall. Open contours represent the down glacier side of that cirque. Some of these cirques are left perched on benches above the main valley floor. Those are called hanging valleys or hanging cirques. Narrow, steep-sided ridges, closely spaced contours divide cirques. Those are called arêtes. And where cirque glaciers have cut all the way through an arête, we're left with a depression called a col. And finally, horns are pyramid-shaped peaks that might be 3- or 4-sided pyramids formed by cirque glacier erosion on multiple sides. This photo shows Reynolds Mountain, which is a prominent glacial horn in the Logan Pass area. Again, cirque glacier erosion on all sides has left this pyramid-shaped peak. So the previous picture showed Reynolds Mountain, a classic glacier horn, as viewed from the Logan Pass Visitor Center. The next picture was taken a little bit farther down from the roadside, again looking south, looking at Heavy Runner Mountain, which is a long arête that runs east from Reynolds Mountain, with a prominent col marking the low spot in that knife-edged ridge or arête. And when we're viewing Heavy Runner Mountain from this direction, we're looking across the broad, shallow cirque on this side of the arête. So again, here's the picture showing this area. Narrow knife-edge ridge, pyramid-shaped peak. Here's our horn. Here's an arête. And then here is the col. In the broad area in the foreground is the cirque. Finally, the last picture from this area was taken near the north end of Hidden Lake, looking back down towards Reynolds Mountain. What does that area look like? Here we have a tarn. Here's our pyramid-shaped peak, our glacial horn, a shallow col, a deeper, better defined col here, through which the trail passes to get down to the shore of Hidden Lake. Here we see a long arête leading away from Reynolds Mountain. That arête is buttressed by several smaller arêtes. Again, narrow, knife-edge ridges left by glacial erosion against the mountainside. This map shows a portion of the Sierra Nevada mountains in California, the Palisade area. Palisades are a collection of tall peaks just west of the town of Big Pine, California. This area is notable because it contains the southernmost glaciers in the United States, the Palisade Glacier, and several other small glaciers that are remnants of a period of cooler climate conditions called the Little Ice Age that existed during the 1800s. Now this area also shows the effects of larger Ice Age glaciers that existed 10,000, 15,000, 20,000 years ago, when the climate was much colder due to a change in Earth's orbit. These glaciers were eroding into relatively resistant igneous rocks, granite and diorite, rather than the relatively soft sedimentary rocks of Glacier National Park. So instead they left relatively shallow cirques. We see a number of broad, shallow cirques in the map area, the most favorable of which have had glaciers reform in them during the Little Ice Age. Separating those cirques are narrow ridges. These are the arêtes. And those arêtes have a number of prominent depressions called cols. there any good examples of a horn in the map area? Here's a good horn. Mount Jepson, a pyramid-shaped peak formed by cirque glacier erosion on 1, 2, 3 sides of the mountain. The other thing to notice about this area is that the glaciers that exist here today are only found on certain sides of the mountains, as determined by the slope aspect. Aspect is the direction a slope faces, as shown by the direction that the contours go down in. In other words, contours in this area are going down towards the northeast. This slope, in other words, faces in a northeast direction. These contours are going down to the north. This is a north-facing slope. Contours going down to the southwest, a southwest-facing slope. Contours going down to the south, a south-facing slope. Contours going down to the west, a west-facing slope. Notice that all the glaciers in the map area are located on north, east, or northeast-facing slopes. Why are glaciers only located on north or east-facing slopes in this area? Well, there's two reasons. One is that the north-facing slopes are better shaded from the sun. The sun crosses the southern horizon. The south-facing slopes get a lot more solar energy because they face more directly towards the sun. In other words, they're warmer. Less solar energy is received on the north-facing slopes. Those north-facing slopes are partly shaded by the terrain, resulting in more favorable locations for glaciers to form. Why are easterly slope aspects favored in this area? Well, winter storms tend to move from west to east. The wind accompanying the storms moves from west to east, and it moves the snow off the west-facing slopes and deposits that snow on the east-facing slopes. Because snow is being preferentially deposited or preserved on north and east-facing slopes due to less solar energy and more loading from the wind, glaciers exist in this area on the north-facing and east-facing slope aspects. This map shows the terminus area of the Kennecott and Root glaciers, which are in Wrangell-St. Elias National Park in Alaska. On topographic maps, glaciers are shown as white areas with blue contour lines. In other words, white-colored areas with blue contour lines are used to indicate area covered by snow or ice. Here's the Kennecott Glacier and its major tributary, the Root Glacier. The dotted areas on the glaciers represent moraines, rock debris being eroded and transported by the glacier, including lateral moraines, terminal moraines, and medial moraines, formed where two tributary glaciers coalesce, turning two lateral moraines into a single medial moraine. So we see the lower portion of the glacier is almost completely covered by rock debris, by moraine material. But we also notice farther up we have several prominent lateral and medial moraines being shown. Lateral, lateral, turning into one medial moraine where the Gates Glacier joins the Kennecott Glacier. Again, another prominent medial moraine is formed here where the Root Glacier joins the Kennecott Glacier. These narrow stripes are also medial moraines formed by tributary glaciers joining the Kennecott Glacier farther upstream. The next slide shows a photo taken approximately here, looking south at the terminus area of the Kennecott and Root Glaciers. What do we see in this photo? We see prominent lateral moraines, coalescing to form one large medial moraine where the Root Glacier is tributary to the Kennecott Glacier. The Kennecott also has a number of smaller medial moraines. These prominent stripes, this is a pretty big one here, representing coalescence of tributary glaciers farther upstream. The flow direction of the ice in the glacier is such that it does not cross the medial moraines. Think of the medial moraines as like lanes on a highway. The glacier ice is flowing parallel to those medial moraines. This photo was taken from approximately the same location looking up the Kennecott Glacier. Again, we see here's a prominent lateral moraine, and we see a number of large medial moraines on the glacier surface. Again, each of these medial moraines can be traced upstream to where a tributary glacier joined with the main valley glacier, and can be used to infer the flow directions of the ice. In other words, the glacier ice is flowing parallel to those medial moraines as if it was following the lanes on a highway. This picture is in your lab instruction packet. It shows the relationship between medial moraines, accumulation area, and ablation area on the glacier. Now, moraines are depositional features. They start forming where we have net ablation. In other words, loss of ice mass. We have to have a net loss of ice to deposit sediment and form a moraine. The dashed line on the photo is the equilibrium line. The equilibrium line separates the accumulation area from the ablation area. Accumulation is where there's a net gain of mass. Ablation is where the glacier has a net loss of mass. Once we move from the accumulation area to the ablation area, we can start forming moraines. We see three small medial moraines on this glacier, and those medial moraines start just below the equilibrium line. So the highest elevation reached by the medial moraines can be used to approximate the equilibrium line altitude. In other words, can be used to approximate the altitude separating the accumulation area with net gain of mass from the ablation area with a net loss of mass.